trust and pray that it's actually recording, and then I do this, and I think we're ready to go. Okay, so guys, this is where we're going to start. But why don't we just get us to the right page so we know where we're going to end? Open your books to 809. You okay? Okay, so guys, just to give us a place where we can reconnect here. Here's where we left off last time. Guys, we talked about, or started to talk about, spontaneity. And we agreed, I think, from chapter 5, enthalpy. We agreed from chapter 5 that the reactions that tend to be spontaneous give off heat, negative enthalpy changes. They're exothermic. Then, guys, as we got deeper into chapter 19, I think we've become comfortable with the idea that spontaneous reactions also create increases in the entropy of the system. The disorder of the system is going up. And we talked about the idea that these can be in tension. That if we've got a reaction that's exothermic and entropy is going up, that reaction is going to be spontaneous. But if we've got competing factors, like for example, our quick cold pack. So guys, if we've got our quick cold pack, we're comfortable with the idea that this is spontaneous, right? But is it endo or exothermic? Endothermic. And that means, given its heat, it shouldn't be spontaneous. But now we've brought in this idea, I hope, that we can explain why this is spontaneous. What allows this to be spontaneous even though it's endothermic? The entropy is going up. And the entropy is going up more than the energy is going up. So this is more disorder creating than it is energy absorbing. Does that make sense? Okay, so we sort of introduced this idea then that these can be in tension. Like with our quick cold pack, our entropy or our enthalpy change would suggest that it shouldn't be spontaneous, but it is spontaneous, and we understand that that's because of delta S. And then we said this: in order to really understand if a process is spontaneous, we need a way to quantify this tension, this interplay between enthalpy and entropy. And we said that the way to do that is Gibbs free energy. And guys, I think the end of your notes, isn't that where it says if Gibbs free energy is less than 0, it's spontaneous. If change in Gibbs free energy is 0, it's at equilibrium. If Gibbs free energy change is greater than 0, positive, then the forward process is not spontaneous, but the reverse is. Okay, so then guys, the question becomes, how do we calculate this? Well, guys, this is it. You can think about Gibbs free energy just like the potential energy of a ball rolling downhill. All spontaneous processes lose free energy. It's sort of the second bullet point up there. All spontaneous processes lose free energy. Free energy always goes down. Notice we've got any and always. Those are those very rare security blankets that we don't get to enjoy much anymore, right? We've got an any and we've got an always. So guys, any process that brings about a decrease in free energy will always be spontaneous. Yeah. Let me, it is, but let me offer this. we're not to the point where we're ready to clarify yet. That's actually how we're going to spend the last half hour of class. No. You're just, no. And I'm glad that you're saying this. What we're going to talk about now, just really briefly, is where do we come up with these numbers? So all you need to understand right now is there's this thing called delta G, Gibbs free energy, and it is a bringing together of enthalpy and entropy. And then what we're going to talk about is this idea that the change in Gibbs free energy tells us spontaneity. If Gibbs free energy is going down, it's spontaneous. Gibbs free energy isn't changing, it's equilibrium. If Gibbs free energy is going up, it's not spontaneous this way, it's spontaneous that way. So we're going to talk about where do these numbers come from, and then we're going to talk about what do they mean given that tension between enthalpy and entropy. And that's, if you look on page 809, that table, is it 809? At the bottom of 809, that's what that table is all about. Okay, we'll get there in a second. Just a second, go ahead. Yeah. Yeah. Yes. Yeah. Yes. Yes. Did you hear that? The answer is, Gwen, absolutely. What you would find out is that that reaction is only spontaneous at certain temperatures. And you can actually make that reaction not spontaneous by changing the temperature. So the last thing that we're going to do today is actually calculate the temperature ranges about which processes are spontaneous. Because you're absolutely right that this whole process, sorry, it's sort of overlaid, but you get the idea. This whole process has a temperature component. And what you can find is that by changing the temperature, you can turn reactions on and off by getting them outside of their spontaneous temperature range. And so I'll teach you how to calculate what those ranges are. Yeah, sadly, I don't think we can do it for the quick cold pack because I don't think I've got the numbers. If we could look up the delta H and delta S for ammonium nitrate, we could do it. Maybe we'll try really quick. Yeah, that could be interesting.
So if you change the temperature of the surroundings of the cold pack and then broke it, then
yeah,
it could be non-spontaneous.
absolutely, it could do nothing. Yeah, but the thing that's interesting is we would have to think it's not necessarily cooling it. Some reactions shut off when they get too hot. And so we need to talk about not just where that magic temperature is, but on which side of it is the reaction spontaneous. And we're going to talk all about that in a minute. Go ahead.
So, are there any examples where it's like the reverse of the ammonia, where it's exothermic, but it's not spontaneous because it increases entropy?
Because it decreases entropy. Yes, absolutely. And we'll look at some examples. So there are definitely reactions that are exothermic, but they don't happen because they're creating a decrease in entropy. Yeah, but what you'll also find is, again, we can turn those reactions on and off, just like Gwen said, by changing the temperature. And we're going to talk about that.
So, this might be too premature, but how is it possible that you can stop a reaction by getting it too hot when multiplying it by a larger number would make delta S more negative?
Not necessarily. What if delta S is positive? And that's the point. And that's exactly Matt's example that he's sort of thinking through hypothetically. If you've got a reaction that creates a decrease in disorder, so delta S is negative, and if you heat that thing up, it becomes less likely, right. So it becomes less likely spontaneous. Okay, so guys, where do we get these delta G values from? Looks familiar, right? If you'd like to take a second and find this equation in your equation sheet, your AP equation sheet, it's right there. It's just this generic products minus reactants form. They could give you the change in Gibbs free energy of formation for the products and the reactants. Again, the ends are missing, like Emma got us thinking. They don't put the ends in the AP equation sheets, but we understand we need to be multiplying by coefficients to make this math work. And that will allow us to calculate delta G.
Wait, so, sorry, real fast. If you got it out of temperature range, what did it do if you broke it? Did they just like sit there?
Nothing, yeah. Wouldn't dissolve, wouldn't do a thing. Yep, yep. Wouldn't do a thing. You guys okay? Yeah, please. Yeah, the Gibbs free energy of formation. Are you sure? Okay. Yeah. And again, guys, they'll just feed you numbers and you just plug them in. Is that okay? No, well, it does mean final or initial, but that's the products and reactants, because products are final and reactants. So it's still final minus initial, but it's products and reactants. Go ahead.
You already talked about this, but what is not standard?
Standard conditions. And understand it's just that technically it needs to be there. It's 25 degrees Celsius, 1 atmosphere of pressure, things like that.
Doesn't it mean something else also in physics?
I don't know. Okay, you guys ready to wrap this up? Not that we're anywhere close to wrapping this up, but guys, here then comes our last thought. We are now ready to answer the question, is a process spontaneous? So guys, to do this, we need to go to the one place that we can turn to identify spontaneity, and it's right there. So guys, let's define our terms. Delta G, free energy. Delta H, enthalpy. Delta S, entropy. We're about to. So guys, this is the way we chunk this. So we clearly, I think, see that this is the Gibbs free energy factor. Now let's talk. What does it mean if delta G is negative? That's spontaneous. You guys okay with that idea? Okay. If delta G is spontaneous, if delta G is negative, that's spontaneous. Now guys, what does it mean if delta G is positive? Right, so we're going to call this non-spontaneous with the understanding that it simply means it does go spontaneously in the other direction. Now, what if delta G is 0? Equilibrium, let's not worry about that for right now, okay? Okay, now let's pick apart the enthalpy term. So guys, we understand that enthalpy is like unto heat. Negative is exothermic, positive is endothermic, right? So, if this is negative, that is exothermic. Do exothermic reactions tend to be spontaneous?
Yes.
Yes. So this lines up. So if we have an exothermic reaction, it also tends to be spontaneous. Is that okay? Do you understand that conceptually? That reactions that give off heat tend to be spontaneous, like the ball rolling downhill. Is that okay? Okay, now guys, do this with me really quickly. Look at it mathematically. I want to touch my board, but I'm just going to have to get close because it's going to mess this up. So guys, if a reaction is exothermic, it tends to be spontaneous, and exothermic is a negative delta H. Now let's make the connection mathematically. If delta H is negative, what will that make delta G? Also negative. Does that make sense? That if this value is negative, that will tend to make delta G negative. So guys, now our concepts and our math are lining up. Because we've made, and I'm going to erase this, so maybe you don't want to do, well, maybe you do want to do this. So we've said this conceptually, that exothermic tends to be spontaneous. But now we're realizing that mathematically this also makes sense, because if this is negative, it tends to make that negative. Is that okay? Okay. Now guys, let's go down and let's talk about endothermic. So if a reaction is endothermic, it's positive. Now let's line up the ideas. Endothermic reactions tend to be non-spontaneous, and a positive value for delta H will tend to create a positive value for delta G. Do you see how those line up? Okay. Now, guys, we've got to be careful. I'm going to switch colors. Now let's talk about our entropy factor. And guys, all of that is our entropy factor. It's not just the delta S, it is the T, negative T delta S. And now, guys, I would encourage you to not write until you see this, but let's talk. So let's talk spontaneous first. So, guys, delta S, remember that's disorder, right? What kinds of reactions tend to be spontaneous, where disorder goes up or disorder goes down? Spontaneous, disorder up or down? Disorder up, right? So guys, if we have a reaction that tends to increase disorder, that tends to be spontaneous. So disorder up, spontaneous. You sold on that? Okay, so what values for delta S indicate disorder up? Positive. So a positive delta S, which is an increase in disorder, tends to be spontaneous. Let's pause, and if you're writing this down, let's let you do that now. So now, guys, let's connect let's connect the relationship conceptually and mathematically. So, and I'm going to erase this because it's going to make a mess, but I'll draw it in now anyway. So guys, an increase in disorder tends to be spontaneous. Are we comfortable with the concept? But now, guys, let's think about it mathematically. An increase in disorder is positive. How does that tend to make delta G negative? The minus T. Guys, let's talk about this. What is T? Temperature. In what units? Kelvin. Why Kelvin? What can a Kelvin temperature never be? Negative. So guys, T is always positive. So put this together. If T is always positive, and if delta S is positive, because we're talking about an increase in disorder, if T is always positive, and if delta S in this case is positive, we've got a positive times a negative. And what kind of values will that create? Negative. Do you see it? So guys, now we have mathematical support for a concept that we already understood. An increase in disorder tends towards spontaneity, but spontaneity is represented by a negative delta G, and that negative delta G is created by a positive delta S, a positive T, and then a negative symbol that makes this entire factor negative when delta S is positive. Do you see it? So now let's do the opposite. Let me erase my arrows. Like so. And now, guys, let's go the other way. Let's talk about a decrease in disorder. So guys, if disorder is going down, what's the sign for delta S? Negative. So now let's connect the dots. I think we're all comfortable with this, right? Excuse me. A decrease in disorder tends to not be spontaneous. But what does the math look like? Well, guys, again, we're multiplying this by a negative t. So now we've got a negative delta S and a t that's always positive and a negative sign. And a negative times a positive times a negative is positive, and that's this. I know that the negative t is on the wrong line, but you get the idea. Do you see the connection? So guys, now we have mathematical and conceptual support for the idea that exothermic reactions tend to be spontaneous, and reactions that create increases in disorder also tend towards spontaneity. Do you get the idea? Okay, so now guys, this is what we've got to do. Let's get rid of this. I'm going to switch to another, and yet hopefully not a horrible color. Let's go green. So guys, the idea is this. Ready? If we have a negative delta H and a positive delta S, that reaction will always be spontaneous. Let that soak in. If we've got a negative delta H, that means it's exothermic, and that moves towards spontaneity, right? If we've got a positive delta S, disorder is going up, that also moves towards spontaneity. So if you've got exothermic and increase in disorder, that reaction is always going to happen. Good? Okay, so now guys, what if you've got a positive delta H and a negative delta S? Does positive delta H lend itself towards spontaneity? No. What about a negative delta S? No. That reaction will never happen. But does that mean nothing's happening? No, it means the opposite is spontaneous. Yeah? Okay, now guys, let's do this. Those are the extremes. Now let's talk about the gray in the middle. What if we have a reaction that is exothermic? Does that tend towards spontaneity? But what if it's got a decrease in disorder? Does that lend itself towards spontaneity? No, so what's going to happen? We don't know. But what will it depend on? Temperature. Now what about the other example? What if we've got a positive enthalpy change? Does that lend itself towards spontaneity? No. But what if we've got a positive entropy change? Does that lend itself towards spontaneity? Yeah. So what's going to happen? We don't know. But what does it depend upon? Temperature. So guys, what we need to do is we need a way to think conceptually about these gray areas where we've got one factor and another factor competing for spontaneity. So how do you do that? Let me roll for a second. How do you do this? Let me show you. So guys, let me clean up this mess and then go here and then go here and then go like so. No, we'll go here. Okay, so guys, here's our reactions, right? Or here's our equation. And you've already got this in your notes, so let me sort of catch up. So this is our free energy term. This is our enthalpy term, and this is our entropy term. And guys, are you okay with the idea that there are 4 possible combinations for these? We just went over them. That's this. Those are our 4 possible combinations. Well, guys, now look at the bottom of page 809. Do you see it? Those are your 4 possible combinations. Now, guys, I'm going to zoom into this. So if you would like to look up at my screen, you can do that. But if you're finding that you can't see, you always have this in front of you in the book. Okay, so guys, let's look first of all at the extremes. Now, in order to have this conversation, I've found that instead of talking about tends to be spontaneous and tends to not be spontaneous, let's use some different words. Good and bad. Okay? Do not use these words on the test or the AP test. But I think if you use the words good and bad, this will help. You ready? So guys, here's what we're going to say. Spontaneous reactions are good. Non-spontaneous reactions are bad. Okay? Spontaneous good, non-spontaneous bad. Now, so guys, this is the way that this goes. Spontaneous good, non-spontaneous bad. So guys, what does it mean that delta H is negative? Is that endo or exothermic? Exothermic. Is that good or bad? Good, right? Because exothermic is good because that makes reactions spontaneous. Okay? Now, what about a positive delta S? Good or bad? Good, because disorder's going up. And that makes reactions spontaneous. So guys, we've got a good exothermic delta H. We've got a good disorder going up delta S. And if we've got good and good, this is always going to be good. You get the idea? This will always be spontaneous. There's nothing you can do to change that. This reaction is unstoppable until it runs out of limiting reactant. Because guys, it's always going to be spontaneous no matter what you do to temperature. Get it? Okay, now let's go down here. What if delta H is positive, endothermic, good or bad? Bad. That's not spontaneous. Now what if disorder goes down, good or bad? Bad. That's not spontaneous. Guys, that means that this thing will never happen. It don't matter what you do to temperature, it ain't gonna happen. But does that mean nothing's happening? No, it means it's just going the opposite direction. Okay? So now, guys, let's look at why good and bad is a great way to think about this. Ready? Negative delta H, good or bad? Good. Exothermic, good, right? Negative delta S, good or bad? Bad, boo, bad, right? So guys, if we want this reaction, hang on, if we want this reaction to be spontaneous, we've got to make the bad thing smaller, right? If you can decrease bad, you could create good. That's why we have police in our town. So if we can make bad smaller, we can make good predominate. So guys, what can we do to make bad smaller? Decrease the temperature. Because the thing that's bad is delta S. And delta S depends on temperature. And in this case, delta S is bad. So to make bad smaller, we can drop the temperature. And if we can drop the temperature low enough, then good, enthalpy, will overtake bad, entropy, and the reaction will be spontaneous. So this reaction will be spontaneous at low temperature. And then when we cross a threshold, which we'll calculate in a minute, then the reaction will be non-spontaneous at high temperature. Go ahead. And the answer is the temperature of equilibrium. And we'll calculate it in a minute. Okay? But guys, do you understand the concept? Some of you are going to forget about this and you're going to assume that all reactions become spontaneous if you heat them up. And you're going, wait, that doesn't make any sense because doesn't heating things make them go faster? Guys, don't confuse rate and spontaneity. Rate is how fast. And yeah, reactions can go faster if they're already spontaneous if you heat them up. But guys, don't confuse rate with spontaneous. If you've got a reaction that's set up like this, you heat it up and it doesn't go faster, it becomes less likely for anything to happen. So guys, this reaction is spontaneous at low temperature. So now let's look at our last potential scenario. Delta H is positive, good or bad? Bad. Delta S is positive, good or bad? Good. So what can we do to make good overcome bad? We need to make good bigger. So how do we make good bigger? Heat it up, right? Because now our good thing is delta S. And if we want good to overcome bad, we've got to make good bigger, and we do that by heating this. So this reaction becomes spontaneous at high temperatures. So guys, you've got to be able to think through this on the test. They will give you delta H and delta S values, and you've got to figure out, is this reaction spontaneous? And if it's not, over what temperature range will it become spontaneous? Understand, the easy ones are these two. If this is negative and that's positive, it's always spontaneous. If this is positive and that's negative, it's never spontaneous. The tricky bit is where you're splitting. And then, guys, the tiebreaker is temperature. If you've got an entropy change, that leads to spontaneity, then heating it up will make it spontaneous. If you've got an entropy change that fights spontaneity, then cooling it down will make it spontaneous. It's that whole good and bad thing. You okay? You get the idea? Okay. So then, guys, the question becomes, where is this temperature at which good and bad switch? Where is this temperature of spontaneity? And guys, we are going to now calculate it. Frankly, I wasn't planning on doing this, but let's actually see if we can make this a little more real world, and let's get some data. So ammonium nitrate, what would be, so entropy of solution. See, this is just positive, negative, or zero. We need a number. Anytime things are posted in a forum, it makes me skeptical.
The other day I was like trying to research on it, and I only could find the package like from people who had done research, and they're like, you can buy this.
Right? Oh, yeah.
And I was like, no thanks.
So this looks like a lab.
Oh, is that how you're using it?
Hey, this looks like the lab that we just did.
You have to teach me how to
How do you
Yeah. Oh, agree.
Do you guys see? Critically evaluated thermophysical property. No. Well, whoa.
He probably just got it by it.
I think so. Yeah. When you have multiple windows pop up like that, be afraid.
Yeah, definitely.
It's all in the science.
So, what about in our books?
It's probably that. They had compounds.
Can't we look up the
Appendix C.
like the heat?
Yeah, but I don't know if does Appendix C include heats of solution?
Yeah, it does. Totally. Yeah. Look, it has the.
Okay,
Oh, no,
if you find data, share it with us.
I was thinking before.
So nothing there. Oh, what's this? Standard molar entropy. Oh, these are just molar entropies. Here, let's try this. You know what, guys? We're going to pursue this for about 12 more seconds, and if this doesn't work, Well, we could calculate it if we,
Wait, what's the link to that?
it's not a bro.
Wait, so we have, wait, do we have,
Oh, wait, is this it?
Oh yeah.
I don't think that this is specific to the system. Yeah, guys, you know what? I would be really interested to do this, but my fear is that we're chasing down a rat trail. So I'm just going to make up numbers. Okay, so let's say that we've got some reaction where A plus B becomes C and D. And let's say that the delta I want to do this in a way that's going to bring out the mistake you guys are going to make in the test. Okay, so delta H for this reaction is negative, oh, you're going to make that mistake too, negative 1.2 kilojoules per mole. And then delta S for this is negative 150 joules per mole Kelvin. So guys, again, I'm just making up numbers. And actually, you know what? That shouldn't be joules per mole Kelvin. Joules per mole, because the temperature is defined. Okay, so the question then becomes this. At what temperature range is this reaction spontaneous? Okay, so guys, in order to solve this, I will, just a second. I'm going to get rid of this because I want that space so I don't slide too far down the board. So what did I say? Delta S, negative 150 joules. Okay, so guys, the question is, at what temperature range is, did I do something wrong? Okay, so at what temperature range is this reaction spontaneous? So guys, the way to approach this problem is, first of all, ask yourself the good and bad questions, okay? So first, is this reaction spontaneous? I'm going to ignore you. We're going to keep going. So guys, is this reaction spontaneous? So let's do good and bad. So negative delta H, good or bad? Hang on. No, guys, don't talk, think. It was Albert Einstein that once said, better to be silent and thought a fool than open your mouth and remove all doubt. That actually was, you guys understand the principle there though, right? If you don't know who said something, just give Einstein credit because that's what everyone does. Yeah, it was actually Mark Twain. But guys, think before you talk. Delta H is negative. Can I use good and bad? Is this good or bad? Good. It's exothermic. Negative delta H values tend towards spontaneity. Guys, I'm not doing questions. Just put your hands down. Negative delta H tends towards spontaneity. We're saying that's good. But on the test, you're not going to write delta H is good. You're going to write negative delta H indicates exothermic, which tends to be spontaneous. In our world, that's good. Okay. Now, what about negative delta S? Bad. That's a decrease in disorder. That does not tend to favor spontaneity. So now, guys, if we want this reaction to be spontaneous, do we need to make the delta S, which is bad, do we need to make the delta S bigger or smaller? We want to make bad little, right? Because if bad is little, then big wins out, and this reaction will be spontaneous. Okay? So what we've now established is that this reaction is going to be spontaneous at low temperatures. Let's pause. Really low. Again, I made up the numbers, but we can still do the math. So guys, do you understand the idea? Delta S does not favor spontaneity, bad, and as a result, we need to make bad little, so low temperatures. You okay with the idea? So now the question is this: smaller than what? At what when we say low temperatures, lower than what? And guys, the answer is this. Reactions can do one of three things. They can go one way, they can go the other way, or they can go both ways. That's equilibrium. And so guys, when we say low, we mean lower than the temperature of equilibrium. That's the switching point. Or if this was spontaneous at high temperature, it would be higher than equilibrium, higher than the switching point. So what we need to do is figure out what that temperature is. Write this down with me. Delta G is equal to delta H minus T delta S. Now guys, what we're trying to solve for is we are trying to figure out the temperature of equilibrium, our switching point. But what can we do to this equation so that we can solve for the temperature of equilibrium? Delta G is 0, because delta G of 0 is the delta G of equilibrium. And now we plug in what we know. Delta H, 1.2 kilojoules per mole, minus T, which is our variable, times negative 150 joules. What? What? Oh, thank you, negative 1.2. So guys, some of you have troubles with this and you should. What's wrong? Your units aren't the same. Guys, enthalpy changes tend to be on the magnitude of kilojoules. Entropy changes tend to be on the magnitude of joules. It doesn't matter which you switch to which, you just have to switch. So in my mind, looking at this, I think this is going to be easier to switch to kilojoules by dividing by 1,000. If you want to go the other way, you can multiply 1.2 by 1,000, but your units have got to line up. So now, guys, we're going to solve. Oh, you know what? That Kelvin actually does need to be there, or else we won't end up with Kelvin as our units in our answer, but we're okay. So now, guys, we got to do the math. So the negative comes over, we get negative 1.2 is equal to, oh no, that's positive. Sorry, you're adding it. I was like, whoa, the units don't work. So we're going to add that over. So we add that to both sides, and 1.2 is equal to 0.150 T. Yeah, so now our negative times our negative is positive. We brought that over. That makes that positive. So we're going to go 1.2 divided by 0.15, and T is 8.0 Kelvin. They cancel on both sides. These cancel on both sides. These cancel. We didn't put units on this.
You subtracted it over and then.
Yep. So guys, the answer is 8. But what does that mean? How do we answer the question? The question is, at what temperature range is this thing going to be spontaneous? And we've identified that it's at low temperature. Lower than what? Lower than 8 Kelvin. So we would then write a sentence that says, this reaction is spontaneous at temperatures below 8.0 Kelvin. And again, I made up the numbers. It's a ridiculously small temperature. But guys, what if you were to say this reaction is spontaneous at temperatures of 8 Kelvin and below? That's wrong, because this reaction is not spontaneous at 8 Kelvin. It's at equilibrium at 8 Kelvin. So notice the subtle difference. There's a difference between saying this reaction is spontaneous at temperatures below 8 Kelvin and saying this reaction is spontaneous at temperatures 8 Kelvin and below. Because 8 Kelvin and below includes 8 Kelvin, and it's not part of the set because 8 Kelvin is at equilibrium. Ashley, go ahead. You do not include the 8. So Catherine, go ahead. No. No, well, but understand it doesn't matter because we're talking about change, and Kelvin and Celsius degrees are the same size. So technically it doesn't matter. But in this case it would matter because our temperatures have to be in Kelvin, so these would have to be in Kelvin as well. But they would work either way because change in Kelvin is the same as change in Celsius. So it's fine either way. So, you guys okay? Concerns? Go ahead. Well, or they'd have you calculate them. We've seen problems like that where they would say, here's a reaction. They would give you the heats of formation for A, B, C, and D, and then you go products minus reactants. And then they'd find another tricky way for you to come up with delta S. It could even be just S of products minus reactants. And then they would ask you the follow-up question, at what temperature range is this reaction spontaneous? And you'd have to take those delta H and delta S values that you calculated previously and then use them. But one way or another, to do this, you've got to have delta H and delta S. They could give it to you or they could have you come up with it. You guys good? All right. Are you glad that you didn't do that through the screencast? All right, so guys, this then is your homework. We will look over this quickly on Thursday and then take our last test.